All right, so kinetics is the first thing that you all will learn new, that it's not covered to its entirety back in Chem 1. Now, so kinetics, there are a few words that we talk about kinetics, and that's one word, speed or rate of the reaction. Okay, now, just like physics or any speed, like meters per second or something per unit time. So when we talk about rate in chemistry, we'll talk about the change of concentration over the change of time. Okay, so so you have molarity per second or per minute in that sense. Unlike physics, in physics we always use the seconds for our unit, but in chemistry you may see seconds, you may see minutes, so it may change as a result. Now, so we will see some graphs, and we are going to pay a lot of attention to graphs in this case later on in this unit. So now, I always like to tell people to do this. Okay, let's go ahead and do this on a piece of paper. Okay. So if I give you a graph, so on the y-axis, it's the concentration, and the x-axis is your time. And the reaction that you are having, it's, let's just say, A becomes B, all right? Simple reaction. Could you sketch a reasonable graph, okay, for the concentration of these two entities? Something reasonable.
So A and B are both on the graph, and A becomes B?
A becomes B, okay? So think about it's like a decomposition reaction of some sort, okay? And let me take a look. Something like that, yes. Okay, something like that. So there are a couple of versions that you may have, and I can draw you a couple of versions. Okay. Now, one thing that I do want to emphasize, it's kind of subtle, but it's very important. And that is, make sure you have a good, clear y-intercept. Okay. For example, for A, okay, let me use blue for A. A should be something non-zero, and then it goes down. Now, where it goes down, I don't care. It can go all the way down to 0. It can become flat. And then for B, it has to be 0.
I don't know. Oh, yeah.
Yeah. Okay. So so that is a very simple yet
complicated,
overlooked detail. Okay. That yeah, when you start the reaction, there's no product. And you're like, yeah, of course. Intersection is not required in this case. So you may also draw a graph that goes like this. Okay. Now, what it's not good in this case. Now, let me show you a graph that is not good.
It is. No, I know, but I didn't realize those were reactive products. I don't know what was happening.
All right. So one thing that it's not good to show would be like this. If you say, well, first, it's not good that you have A from the below and B from the top. Okay. And so something else that's not good is that if you show that A goes down really quickly, and somehow B is kind of flat. Yeah, because the ratio here, it's 1 to 1. So that means the slope of the rate of the rate of appearance would have to equal to the rate of disappearance in this case. Okay. Now it may not be the same. It may not be the case every single time because it all depends on the mole ratio. So I think on your packet there are a few questions about. They give you the rates of appearance, and you have to find out the rates of disappearance and appearance. That's just pure mole ratios, and I'm not going to spend too much time talking about those. Okay.
Like in this case, if the ratio was like 2 to 1.
Uh-huh.
Like A was 2 and B was 1.
Okay.
Then you would have the steeper slope with A. Right?
2A to 1B. So yes, you consume more A and then you produce smaller amount of B.
Yeah.
Yes. Okay. So make sure you also take that into account. Maybe you have a few slopes to choose, then take that into account. Okay. Now, the key thing of this unit, it's about the term rate law.
Oh, yeah.
All right, now, a little story that I want to share with you here. This is also the unit that covered in the first semester, and I told you that I did not take the AP Chemistry in the first semester. I had no idea about these materials when I was reviewing myself. So it was tough to learn by myself. And then when I finally learned it, when I went to college, then I was like, oh, that's how it makes sense. Now, so let me just go ahead and tell you what rate law is. Think about it as an equation. Okay, that represents rate. Okay, now later on, just a little preview of what you will see. Later on, you will also see something called the integrated rate law. Okay, integrated rate law. And for the integrated rate law, it's not the same. Let me give you more specific difference between these two. These are both equations, but integrated rate law is the one that is with time. And rate law does not have time. Okay, and I'll show you what it means later on, but just to show you that there are a few terms that are in your horizon, so don't get those confused. Now, if you have a reaction of, say, A, B to make C and D, okay, for example, okay, and it is possible, I'm just going to give you an example, right? It is possible to have something like this. All right, just an example, by the way, okay? Okay, I'm going to explain this one by one. So this is the equation that that represents the rate of the reaction. And when you look at the rates law right here, you can see that we only see the reactants, never products. Okay.
It was like it only depends on the composition of the reactant.
Never products. Okay. All right. K is what we call the reaction constant. And now the reaction constant, this little K thing, it's a little bit mysterious. Now, let me also introduce a couple of simple words that I want to clarify before you get confused. This reaction constant, it's going to be the same for the reaction. Now, we will show you a table with multiple trials of the same reaction. The K doesn't change as long as the reaction is the same reaction. Okay? So for example, okay, let me go ahead and give you this little table right here. Yes, you will see something like this. All right, so you see this right here? You have 4 different experiments here. Okay, 4 different experiments of the same reaction. So the K would be the same for all these experiments. They're just little different trials for the same reaction. Okay?
So it's like static friction, like it varies from object to object, right?
Yes, different reactions would have different K, and different temperature would also change the K. All right, so are we good so far?
Yes.
Now, then, so again, the concentration will only be the reactants. Now, you may see something like this. And what does it mean? Okay, now, let me give you the lingo in this topic because it gets very specific. Okay, so we would say reactant B is first order. Okay, now what does it mean when we say first order? It means that if you double concentration of B, nope, then you double the rate. So that is linear, first order.
Yeah, like a proportional relationship.
Yes.
Directly proportional.
They are directly in a linear way. So if you double B, you double the rate. If you halve the B, you halve the rate.
And like, if B is the first order, obviously A can't be. So
we'll get into that in a moment. Yeah, and this is what I am afraid of, is that we are trying to move too fast, because there are some numbers that could be confusing, and you have to be very clear about the definition so that you know when to use some numbers and when not to use the numbers. What about A? Well, if B is first order, guess what? A is second order. So you can judge the order based on the exponent. And why do we call A as a second order reaction? Because if you double the concentration, you will quadruple the square of the rate, the square of the change.
Yeah,
if you are tripling the A,
then
9 times. Mm-hmm. Probably. Yeah. Yeah. So that's the little lingo right here. Now we will also look at the overall reaction order, which is an addition of these two. In this case, we'll say the overall third order. 1 plus 2, 3. That's a very good question. That is a very, very good question. And that question leads to the discussion of our little K that I started but did not finish discussing. So why is this K a little bit mysterious? Because there would always a question. There would always a question that asks you, could you tell what the K is and also provide the appropriate unit? Why do we care about third order? Well, because it's about to show you the why. Now let's take a look at the unit. For the rate, right? We were talking about rate could be molarity per second, right? Okay, and of course the time unit could change, but let's just say seconds for now. And this is an equal sign. And if you know me, you know how much I care about equal sign.
Yes.
And what about the units from the concentrations?
Molarity for
Right? So now the mysterious part is,
second.
what is the unit? What must the unit be for K so that it's equal? We have to have a second in the denominator.
The m squared times the m cubed. Square cube root m. No, put it at m squared on the bottom.
Mm-hmm.
Because m's cancel. And then you level whatever, and then you level. Oh, that was good. I like that.
Okay. All right. So that's how we judge the unit for K. Now, and since we're talking about this, let's go ahead and imagine these scenarios. Okay. So overall reaction order. Oops, sorry. My handwriting got a little bit ugly. Unit of K. So we just discussed the overall third order, right? And the unit is 1 over m squared times s. Now, what if overall order is first order? So for example, the rate law could appear like this. Rate is equal to K times A. If it's overall first order, that means the power, it's only 1. Okay? So we'll,
It's just second. 1 over second.
1 over second. And what about overall second order? So it could look like something like this.
M times second.
Okay, you can have
1 over m.
1 over m times second. So this is the mysterious part that I was when I was a student, I was like, wait, what? So the unit could change? Yes, the unit.
Easy though.
It is easy, but you have to acknowledge that the variability of the unit.
So that equation is not like a constant equation. It just changes based on the
Reactions.
On the reaction.
Yeah, it could change, and so that's a rate law. And when we say the rate law, we would keep the rate as the word rate. You don't put a number right there. Okay, you can keep the K right there, unless they ask you to find it. Okay, but your job is to find out the exponents. So how do we find the exponents? So let's go ahead and take a look at this, okay, at this table. All right. So you will be given this kind of table, and this is the easiest kind of table you would see. And you would ask a simple question: how am I going to use this table?
I'm going to use it by determining the concentration. And if we're plus another concentration. No, but you do K. You find out K first, right? But you find the concentration to equal that to the rate of formation and find
Nope. So now.
But you said K is the same for all of them. So if you have one full reaction, which you have 3, you can find.
So let me go ahead and share the journey of finding it. Now, remember how we make the assumption, not the assumption, the conclusion right here? How do we describe the first order and second order? And by the way, something that I did not say earlier, it is possible to have something called a 0 order. That would look like
0 order. K. Yeah.
That means if you double your concentration,
then
what would happen to the rate?
Nothing.
Nothing.
Because there is no concentration.
Okay. Just like how I'm.
Well,
No. Now think about this. Your stomach. Does the reaction rate or digestion rate? Does the digestion rate of your stomach get faster when you eat more?
I wish.
Yeah. So you can consider that as a way to understand what it means to be a zero order. Okay, it doesn't change even though the concentration changes. So that will be zero order. Now, so in order to tell, now I'm going to show you two ways. One is to just look at the table and tell. But the second thing that I would like to share with you is the actual formal way of showing. Ready? So in order to judge, okay, you would have to hold one reactant the same concentration.
You should have two experiments with one reactant that is the same.
So then we look at the other reactant. We say, oh, look at this. Look at the nitrite ion concentration. It doubles. So times two, and then what happened to the rate? It also doubles.
So the product is 2 and 2.
So the exponent is 1. First order. If it doubles, that's also double. Right? That's what we said about being first order. If it doubles, if the concentration doubles, the rate doubles.
Yes. Oh, yes.
Linear, right? If the concentration doubles, the rate doubles. Okay? All right, now, and then we look at, so now we are settled with the nitrite ion order. How about our ammonium ion order? Which two experiments should we look at?
Oh, 2 and 3 because it's double.
Mm-hmm.
And also because it's the same concentration. Right?
So first, the same concentration. So this one times 2, they are also multiplied by 2. So that's the first order. So if I want to ask for the rate law, ta-da, that's the rate law.
So that's first order because it's just doubling.
Yeah.
And it's doubling concentration.
Yeah. Mm-hmm. Are we good? Now, so that's how we can just use the table, scribble something down, and get the exponents. But how are we writing it down with work? Now, this is how you do it. So let's just say we consider experiment 1 and 2. So what we would say is this: rate 2 over rate 1, it's equal to K NH4 plus times NO2 minus over K NH4 plus and NO2 minus. Well, hold on. Sorry, my bad. Thank you for reminding. Actually, we do not know. We do not know the exponents yet. Okay, so that's the second way the formal work that I'm showing you now. Well, we will. So this is the how. So 2.70 times 10 to the negative 7 over 1.35 times 10 to the negative 7. Now the K, since they're the same, they cancel each other out. And the concentration of ammonium, they're the same. So they got canceled out too. Right? Oops, sorry. So they cancel each other out. So what you have here, it's 2, it's equal to, oh, sorry, my bad. I wrote the numbers backward. Should be these two switched because I put experiment 2 on top and then experiment 1 in the bottom. And this will be 2 to the n power. All right. Now, let me say one thing right here. A good question to ask is, hey, Mr. Chan, why would you put rate 2 over rate 1? Can I put rate 1 over rate 2? You could, but I would like to put rate 2 over rate 1 because big number over small number, you got a nice number 2. It's easier to compute. Okay, and then you would all, now the exponent that we see, it's going to be an integer. So that's how you find out your exponent quantitatively in an acceptable way. Now, if you just scribble and then write the rate law, you are not going to get full credit.
So it's products that, reactants?
Always the reactants, and the table will always give you the reactants. Okay? Now there's a question right here. It says, hey, what's that concentration?
Okay, you can look at 3 and 4. The concentration of NO2 doubled.
But the rate is not doubled. The rate is somewhat different.
Well, then you set it up the way you did it. So rate 4.
You could, or you can find out the K value first. Now that we have now assuming that we did all the work and we have the rate law right here, that means we can find out K. We can simply say, oh yeah, just go ahead, pick any experiment because the K value is going to be the same. Oops. Right? So you can go ahead, find out the K value. So you will use a calculator, 1.35 to the negative 7th power, divided by 0.1, divided by 0.05. So K is equal to 2.7 times 10 to the negative 3. And the unit is 1 over ms. All right. And then, overall second order. Overall second order. And then you can go ahead and use the K and the rate law to calculate. Then we say, so the rate is 4.00 times 10 to the negative 7. And this is the K we have just calculated. And then you have a missing unknown for the concentration of ammonium ion. And you do know your nitrite ion concentration. So it becomes a very simple calculation to handle. So the ammonium ion concentration is going to be 7.4 times 10 to the negative 3 molar. Okay? All right, so now there's one thing I want to emphasize here. Now we are going to see some more rate law stuff, and it becomes a little bit tempting to relate the exponents to the coefficients of the equation. Okay, now I'm not saying don't do that. I'm saying that you can only do it in one specific situation. And that is, the question has to mention that the reaction given is an elementary step. All right, now what does it mean? What does it mean? Now, an elementary step, it's like the little steps of a multi-step reaction. So the reaction that I'm showing you here, what you can consider is that, oh yeah, this equation right here, consider this as an overall reaction. But there's a lot of stuff happening in between, in the middle of the process. But that is just the overall look.
And then with each redox an elementary reaction.
I would not constantly say that because there could be more than that. Okay, yeah. So there are a lot going on in between the ammonium ions and nitrite ions. So therefore, we will not use the reactants, the coefficients, to show it. Okay. Now let's take a look at this and see if you can handle this calculation. It's a little practice.